Hi everyone, this is Tyagarajan, retired Deputy Chief Engineer from Indian Railways. The previous video I had been discussing something about the concept of functioning of LWR and the role of temperature, in what way temperature affects the LWR, CWR functioning, and the setting up of internal forces. Okay, all those things we had been discussing, and this video in continuation to that. Okay. I'm going to discuss something about the laying of LWR. What are the requirements we need for laying LWRs and perimeter locations. So all those things we are going to discuss here now. Okay. So we have Indian Railway Perimeter Manual. So they are given a lot of stipulations, provisions they are given, and I am going to discuss that. Just I am reproducing whatever the LWR manual says. That portion says, and with a little explanation I am going to discuss now. Okay. So, as per Indian Railway Perimeter Manual, we must have only LWR, CWRs. Okay. Of course, in our nowadays all sections almost we have LWR. Okay, because of your disadvantage of the fish plated joints, what we have already discussed. So even there's still some few sections you may have, and those sections also we have to identify what to go for LWR or CWR. And also whenever we go for new lines and doubling and gauge conversion, and we must have LWR. This and all now presently it's made compulsory like. Okay. And also even existing tracks, whenever we plan for through rail renewal and complete track renewal, that time also we are nowadays planning for LWR, CWR only. So we want to avoid as maximum the fish plated joints in the running track. Okay, and also in the yard lines, yard also many yards still have the fish plate track. Fish plates we have a lot of headaches, so we want to avoid. In yard line also nowadays we are planning for this one, converting existing free ride track or SW track into LWR. Particularly in running lines and running lines, provided the condition of rails, sleepers and fitting should be alright. So to the approval of Chief Track Engineer, we can convert those lines also into LWR. Okay, this is something about the general provision. This coming to the other the locations, perimeter locations. For example, suppose we want to have the track in between X and Y, the particular stretch. So we may want to have the LWR. So there will be a lot of obligatory points we will come across. So namely the curve. So curve, normally sharper curve, we cannot go for the LWR. And also the gradient, steeper gradient, we already are avoiding it, and level crossing. On bridges, of course, bridges we have ballasted bridges and girder bridges, and here also we have a lot of limitations. Okay, then points on crossings can go, but however these are the obligatory points. So these things we are going to discuss. Curvature means what's the sharpness, limitations, and gradient, what is the limitations and all. These things we are going to discuss in the coming slides. Okay. So coming to the curve, that is alignment, normally suppose we have 60 gauge rail and 1660 sleeper density, we can go up to 6.5 degree of curvature in zone 1 and 2. Okay, up to 6 degree in case of zone 3 and 4. These are the provision available in the manual. Sharper than this we cannot go. Okay, the zone wise they are given. And also joining with the steep gradient, the steepest gradient they are given. So gradient you have to consider. If it is it is a plain track, normally 6.5 degree in zone 1 and 2, and zone 3 is 6 degree. Suppose we have the curvature with gradient, this is the limitation. So 5 degree with the 1 in 65. This sharpest permitted grade, the steepest gradient. This is the provision available. This is supposed to follow this. Okay. Because Y means already it is a designed curve we have, but whenever there is a temperature increase, there will be setting up of compressive force. That will also try to give the buckling effect, that is bursting force. So joining with the designed curvature should not get aggravated and buckle. That is why if the sharper curvature is there, more sharpness, more will be the bursting force. That is why you want to restrict the curvature sharpness. So most at the same time we are providing the shoulder ballasting and all strengthening and all we are giving, but even then the sharpness we are limiting it. So this is the restricted curvature as per the Indian Railway Permit Way manual. And 1540 sleeper density in the 50 gauge rail. This earlier we are having 50 gauge. Now of course everywhere we have 60 gauge rail. Whenever we do TR or CTR we go for 60 gauge only. But in existing track still we have some places we have 50 kg 1540 sleeper density. In this case the curvature can go up to 440 meter. That is 4 degree curvature. Up to 4 degree we can go. And also in the case of zone 1, so they are given some relaxation to 350 meter radius. So 5 degree, up to 5 degree we can have some relax. That means 5 degree. This thing. This 50 gauge 1540. Zone 1 they are given 350 meter radius. Up to 5 degree we can have. Duly satisfying the following conditions. Okay. Because zone 1 normally already discussed, zone 1 temperature variation is, it's less. That is why this little relaxation they have gone out to 5 degree. We must ensure 300 mm clean ballast cushion. Okay. Of course, so normally, the curvature in LWR track and we are giving 150 mm extra. So normal shoulder which is 350 in a straight track. But when we are, in the case of LWR and curvature, 150 mm extra we are providing. 150 mm extra, that is 500 mm. But in case of, we want to have the zone 1 350 mm radius in 5 degree, we must have extra mm. So total 600 mm shoulder ballast we must ensure. So this is something about it. Okay. Then reverse curve, of course. Reverse curve, is also very critical location because combination of two curves but reverse direction. The junction point, common tangent point is so dangerous, serious. So that location should be taken care. Okay, that is why in this case two curves are there. Normally, if it is considered as a reverse curve, there is no straight in between. It's called a reverse curve. Okay, no straight. If that is the case, what you do? This location is as already told is critical. So this location we have to strengthen the shoulder ballast. Here this is shoulder ballast, this is shoulder ballast. Okay, the shoulder ballast we have to increase to 600 mm. So I already told 350 mm normally in a straight track and 150 mm normally we are giving the extra. But here one more mm we are giving extra. So totally 600 mm shoulder ballast you are ensuring in the the common tangent point, where the common tangent is there. This side 100 meter, this side 100 meter. Okay, but this is a common tangent point. The approach of this one, the both sides 100 meter and 100 meter, we must ensure the shoulder ballast of 600 mm. We must ensure. And also sometimes we have the straight in between the reverse curve. Suppose straight this straight whatever straight available, if it is more than 50 meter, we need not consider as a reverse curve. It is separate curve, normal provisions will apply. But when the straight portion is less than 50 meter, so in this case again as earlier discussed, 100 meter both sides, that is from the center of the straight, this 100 meter, this 100 meter, we must ensure the extra shoulder ballasting, that should be 600 mm. Okay, this should be followed. And coming to the gradient, in general, we want to have LWR should not be steeper than 1 in 100. This is general provision. But however, we can go for up to 1 in 65. In case of zone 1, 2, 3, steeper gradient we are permitting up to 1 in 65 with a curvature of 5 degree. In zone 4, be steeper than 1 in 80 with a 4 degree curvature. Okay. And as I discussed, zone 1 and 3 is little okay, but zone 4 is critical than your zone 1, 2, 3. That is why here restrict to 4 degree, and also the steeper gradient, steepness also they have kept 1 in 80. This is something about the steepest gradient permitted overlaying LWR. Further, this why this we are restricting the gradient, steeper gradient. You all pretty well know. Normally, when our trains are climbing over the gradient, the heavy load, so there will be, it has to apply more tractive load for effort for climbing over the steep gradient. At the same time, when it is going in the down gradient, so sometime it will, there will be more braking force will be there. So both the forces, steeper gradient will be excessive. It will magnet of it will be more. That force will act on the rail. Ultimately, already the rails will be having subject to high forces, high compressive force, high tensile force, the extreme cases, either T maximum or T minimum. Adding together these forces will create a situation worse. Sometime, if it is excessive, it may result to buckling or it may result to fracture in both extreme cases. So that is why, so we want to limit the steepness of the gradient. That is why maximum, the steepness we are restricting, we are going up to 165 in zone 1, 2, 3 and zone 4 we are restricting to 180. Okay, this is something about it. Okay. So coming to the LWR and bridges, see, LWR, CWR can be continued over the bridges with ballasted deck without bearings. So ballasted deck bridge we can continue, okay, our LWR, CWR, like slabs, box culverts and arches. That means, the RCC slab bridges we have and PSC slab bridges we have, those bridges, the track structure on the bridges will be similar to the track structure what we have in the formations. So completely sleeper, ballast, everything will be there. There is no change of, track structure. So in this case, we can carry through LWR over those bridges. There is no restriction. And coming to the unballasted deck bridge, unballasted deck means that is girder bridges. So normally there the track structure is different. We don't have any ballast and all. It is only we have a rail sleeper frame. It is having the rail free fastening and the entire frame is fixed on the girder. Okay, fitted. So this is different because as far as LWR is concerned, we must have the elastic fastening and this where some resistance should be offered for them controlling the movement of the rail. But here it is absent. So we are providing only rail free fastening normally on the girder bridges. The why we are providing rail free fastening means you all will be knowing, because there should not be any interaction between the rail and the bridge structure. So we want to isolate it. So whenever there is a temperature variation, so will undergo expansion contraction. So rail will undergo expansion contraction like the bridge structure expansion contraction. So suppose fixing together, there will be more interaction. Sometimes it will result to unequal setting up of unequal forces. Sometimes it may transfer to the bridge structure. It may weaken the bridge structure. That is why we don't have, we are not providing any elastic fastening in the girder bridge. So rail free fastening we are providing it. And this rail free fastening, normally it is not comfortable for the LWR truck because, for example, suppose in case of any fracture on the rail, girder bridge, in the middle of the bridge there is a fracture. What will happen? So because of the fracture, it is having rail free fastening for the length of L. Let us assume the overall length of the bridge is L. Once it is a fracture, full of tensile force, there is a fracture takes place. What will happen? It try to contract. So once contract, there will be a development of gap. There will be gap at the fracture portion. That will be proportional to your length of the bridge. For entire length, you have the free fastening. There is no resistance offered by the sleepers. So in this case, it will be LR40 normally. So the maximum gap will be there. More gap will be there. Apart from the gap due to the breathing, like a breathing, the approach of the bridge, we have sleeper, ballast, everything. That also will contribute some, contraction. So that is why track over the bridges, which is having the rail free fastening, will contribute more for creating a gap in the case of rail fractures. Okay, this normally is unsafe. That is why we are limiting. So more the overall, more will be the gap. That is why we are limiting our overall length of the bridges. Here we will see what all the different situation we have and how much overall length is restricted for each case we will see here. So first case is this one. Normally single span not exceeding 30.5 meter and the girder will have the slide bearing on both sides. Both sides slide bearing. The expansion contraction will be, the girder will be, both sides will take place. But single span not taxi 30 meter, this is the first case. But rail, of course, as I told you, we will have rail free fastening on the bridges. And second case, similar to the previous one, where we are having some box anchoring, some portion of sleeper for track. That means some 4 sleepers will be box anchored. Suppose it's having slide bearing, both ends there will be expansion, contractions permitted. Suppose centrally we are holding, central 4 sleeper we are box anchored, what will happen? There won't be much interaction, because only central portion only we are holding, we are anchoring, so that the expansion contraction of girder will take place, and both ends will not have any the interaction of the rail. It will independently, it will be expanding, contracting. Okay, there won't be any problem. So in this case, what is the maximum overall length we can permit? Okay, the second case, because of the box anchoring, we are controlling the launch movement of the rail. That means the creep movement. Suppose movement of traffic is there one side, means the entire rail try to move. No. So because of the anchorage what we are providing, we are not permitting the launch movement. At the same time, the girder we are permitted to independently expand, contract. Okay, and both ends without having any interaction with the rail. Okay, this is second case, and both cases will see what is the overall length. So we have the 4 zones, zone 1, 2, 3, 4, and 60 kg, 50 kg for zone 1, 30, 45 in the first case. But single span not exceeding 30.5 in this case. This is applicable only in the first two cases only. The single span not exceeding 30.5 meter. Even the other zones and all, maximum overall length itself restricted to 11 meter and 27 meter, 60 kg, 50 kg respectively for all 3 zones. Zone 2, 3, 4. Only one only we are able to go more. Okay. And coming to the case 2, similarly, see here, like previous this case, but here we are anchoring some 4 sleepers. We are central 4 sleeper. We are providing anchorage. So that is why some resistance, some holding the rail, not to permit any launch movement. In this case, for zone 1, 77 meter overall length for 60 kg and 90 meter for 50 kg, and zone 2, 60 kg 42 meter and 52 kg 58 meters, and rest of the zones, that is zone 3 and 4, we have only 23, 43 maximum 60 kg 50 kg respectively for both cases. Okay, this is something about the maximum length, overall length we are permitting for carrying through LWR in these cases. Okay. However, we must ensure the breathe length, the bridge should not fall in the breathe length. Okay. Because where we are permitting breathing, in this case we have girder bridges which is having rail fastening. Since there is no offering of ballast resistance, so the length of breathing will be more. So length of breathing length will be more. Once the length of breathing is more, automatically the gap, the expansion contraction will be more and the CG. So that is why we don't permit breathing length to fall in the, the bridge or bridges should not fall in the breathing length. Okay. And also in this case, the approach of the bridges of 50 meter on either side, should be well anchored. Okay, well anchored, well ballasted, compacted, and also the ballast should be heaped up to the foot. Extra ballasting must do, like that. Firmly we are keeping it. Okay, so that even though there is a fracture in the girder, this approach should be sound, should be sound enough to control the movement. So that is why this is to be properly looked into the approaches, putting some well ballasted and compacted and good consolidated condition. Okay, this is something about these 2 cases. And another case is, this case we will see here. LWR, CWR may also be coming over the bridges with the provision of SCG at the far end of the approach. Suppose this case, what we will do, we can permit LWR on the bridges. This case, what will happen, the bridge, enter bridge will be in the breathe length, providing SCG on the one end. Okay. This is one type. In this case, what will happen, as I already told you, since it is falling in the breath length, there will be, since it's rail free fastening, since no offering of ballast resistance, that is why the breathing length will get increased, and ultimately once the breathing length get increased, automatically more expansion contraction at the SCJ. So that is why in this, if that is the case, what we are permitting, we are in this case also we are restricting the overall in the bridge. But here, since due to the excess gap we will face in the SCJ because of the this situation falling in the breathing length in the rail free fastening condition. So we have to go for a special SCJ which is designed for maximum gap of 180 mm. Okay, this is one case, and other case designed for 120 mm. So two cases are there. And the first one, the first one, zone 1, 2, 3, 4, all 4 zones, there is a overall restricted. No, zone 4 is a critical zone. That is a 50 meter only we are permitting it. Zone 3, of course, 70. Zone 2, 110, and of course, zone 1 is okay. That is 160 meter. So these are all the limitations they are given for this condition. Provided we must have the SCJ of this type. Okay. And another type, we can go for 120 mm SCJ we are providing, and we are restricting the overall length 20 meter in zone 2 and zone 1 only. It is applicable only for this situation, only for zone 1 and 2, not for zone 3 and 4, since they are critical. Okay. However, this is the case, initial gap we are supposed to provide this much. Normally, our SCJs we used to provide initial gap of 40 mm. Okay. But here in this case 70 mm, 190 mm, 75 mm zone 3 and 4, and zone 1 and 2 65 mm initial gap when we are using 180 mm gap. In the case of zone 1 and 2 120 mm gap SCJ, the initial gap normally as already was regular. This is 40 mm only. Okay. So this is to be followed. Okay, this is to be followed. And another case, we can go for welding the rails peer to peer. Another situation, this is also possible because when we have the major bridges, span also will be a very large span when we have. In this case, the peer to peer can weld all the rails. Okay, all the rails. We can eliminate all fish plate joints on the bridges, so that running will be all right. Because of the fish plate track, there will be noise. In every joint there will be knocking sound. In this case, what we are doing? Peer to peer we are welding and providing SCJ on the piers. This case. Okay, this is one more case is there. In this case, there is also some restrictions like we will see in the subsequent slides. What is the maximal length? We will see. Okay. Here, this is two cases how it is. There is, as per Indian Permanent Manual, they get some detailed explanation through the drawing, and the two cases, that is peer to peer and SCJ providing SCJ the far end of bridge. Okay, this is case. And the peer to peer providing the span and all, I will tell you later in the second slide. We will see the maximum span and all. Okay. Here there are two situations will come across. One situation is the girder placed on a bearing, and one side rocker bearing, other is roller bearing. This rocker bearing means you do not permit any launch movement, only rotation movement will permit, and no launch movement will not permit. But here slide, roller bearing, it will permit launch movement. So okay, this is another thing. This thing is both side we are having slide bearing. So both side it will permit expansion contraction. This side expansion, this side here only this side expansion will not permit, only one side contraction. So in this case, we are providing SCJ at every pier, in between all the joints we are welding it. Okay, all the joints we are welding it. SCJ we are providing the pier. But in this case, since it is rail free fastening, some holding must be there not to permit any launch movement of the rail. Otherwise, due to traffic movement, rail will try to move on one side and jam. The SCJ gaps and all will get jammed. That is why to avoid, to restrict that, we want to have some holding. That is why we are doing box anchoring. Some force sleeper we are box anchoring. But in the two situations we are doing the box anchoring. In this case, suppose this case we take, here it is a rocker bearing, here it is a roller bearing. Here it is not permitting the any expansion. Here only expansion permitted. That is why the portion and the point, the location where it doesn't permit the expansion, this one we are holding it. So once we are holding it, this will not affect the expansion of the girder or rail, okay, whatever maybe, okay, because we are holding only this portion, fixed portion we are holding, we are providing anchoring. This is the case. In another case, since Slide bearing we are providing both ends. Expansion and contraction will be both ends. That is why what we are doing, we are providing box anchoring in the central force sleepers. We are doing, there won't be any problem. It will not affect the expansion contract the bridge or rail, since we are box anchoring in the middle of the girder. Okay, this is something about it. So you are supposed to follow that. Okay. And another case we have seen, on the far end of bridge we are providing SCJ. This we are providing it. Here entire bridges will be having rail free fastening, but it is on the breathe length. So because of the rail free fastening falling in the breathe, definitely there will be more expansion apart from the breathe length of the ballast. This is the breathe length, it's directly proportional to the L. More the L, more will be there. So there will be more gap will be there at SCJ. That is why we are providing the special SCJ at the approaches. Whatever SCJ we are providing should be 15 meter away from the abutment. Okay, we are providing SCJ. This is something about this one. Okay, so next case, we can provide the welded rails in a single span bridge. Okay. Again, I already told you, using the special SCJ with the 180 mm gap SCJ. Okay, this is also permitted, but in this case also, the maximum over length is restricted. So the same thing we can apply for the peer-to-peer. Okay, just like a single span. Okay, that they are not mentioned, there, but however, this thing, maximum length we are single span, same over length we can permit when we go for peer-to-peer when welding it. Okay. Here zone 1, 2, 3, 4 they have for various overall length, zone 4 75 since critical, 87 zone 3 and zone 2 110 meter and zone 1 140 meter. This is all single span. Okay, when we have the single span bridge, we can completely weld all the joints and providing SCJ on both abutments. In this case, we go to use for SCJ designed for a maximum gap of 180 mm. Okay, but that SCJ should be provided 30 meter away from the abutments, both abutments. Okay. Is to follow. This is something about it. And also, suppose whenever bridge, we cannot carry through. Okay, it is not the falling in our this one stipulations provisions. In this case, the bridge should be isolated. That bridge should be isolated with LWR. So LWR should be terminated in the approach of the bridge and isolating the bridge, and again SCJ we are providing, we are starting the LWR CWR like that. Okay, but in this case the minimum length of isolation must be 30 meter. Okay, approach both sides 30 meter we must have the isolation. Only after that only we must have the SCJ. That portion should be well ballasted, well anchored. Okay, well strengthened. Okay, that is something about the isolation process. So this is about the LWR on bridges. And coming to the track structure, this is whatever the thing earlier we have seen about the obligatory points, whatever obligatory points we will come across, and for various obligatory points. So what are the limitations we have seen? Okay, that we are supposed to follow. And coming to the track structure, see, track structure means what? That is we have the formation and ballast, a sleeper, and rail free fastenings, and rail sleeper fastenings. These are all the complete track structure we have. But foundation is our formation. So the form should be stable. Okay. Whenever you want to have the LWR, but the LWR CWR already we have discussed, the extreme temperature range, that rail will have the internal force. Setting up of internal force should be there. In case of temperature increasing trend to going to extreme, there will be setting up of maximum compressive force. Similarly, when it goes down to T minimum, there will be setting up of tensile force. Okay, they both are critical. The upper side will results for buckling, lower side will results for rail fractures. So in that case, since it is that is why we have to take care our LWR this one, and firmly we are keeping it. And that is why the foundation is very important. Suppose foundation is a weak, because nowadays and all, whenever we are going for the new construction, we are doing pakka well soil we are using, and also blanketing of minimum 1 meter we are providing it. And so the earlier cases and all, those old formation and all, normally it will be in some form, we don't know how it was constructed, it was made. and many locations in many places there will be this one formation problem. So often that location will run down. Frequently we have to pack and see all those things. Frequently we will be facing the problems. But as far as the LWR is concerned, it should be the formation should be sound, because once the formation is, what will happen? The ballast will penetrate into the formation. The ballast deviation will take place. Ultimately, to the offering of ballast resistance will not be that much. It required a level, and it will cause for something. In extreme case, it will to buckling. Okay, and moreover, frequently, either we have to inspect and we have to go for ballasting. Frequent, we have to go for frequent attention. We have to. All those things will take place. That is why we want, before laying LWR, being the critical nature, you must ensure before laying the formation should be all right, and identify the location where you have the troublesome formation. That location should be rehabilitated. Okay, doing some various treatment. We have formation treatment, some rung blanketing used to do. So many normally rung blanketing nowadays we are planning everywhere. Okay. This thing to be done, and see that it's completely stable. At the same time, this CIS also, the formation profile also, there should not be any CIS erosion. Sometimes, many locations, even though we can see, many places there will be, there will not be a standard profile, formation profile, and there will be erosion of CIS. Once there is no CIS available in the formation, whatever ballast we are putting is sliding, there will be a deficiency will be there. Ballast deficiency normally we are not supposed to permit in the LWR. That is why that also we have to look into. Any CIS making up, is there, we should to make up the CIS to the standard profile, for supporting the ballast, going the lateral distance. Okay, that is something about the stable formation. Okay. Then rail section, minimum rail section, we are supposed to use only 50 kg nowadays. So of course nowadays wherever you do TRR, and all, we are going 60 kg. However, the existing rail, 60 kg, 50 kg we may have. It's okay anyway. Minimum rail section was 50 kg. Suppose the yard line still we have 50 kg, that if we want to weld it, we can weld it, no problem. 50 kg is minimum rail section. And no different rail section in only LWR, CWR. Suppose we have, we want to weld between X and Y station, and X and Y full same length, same cross section should be 60 kg. We cannot, weld 60 kg and 50 kg in one LWR. We cannot convert. For example, suppose we have 50 kg rail section between X and Y station. Okay, but we have the TR complete track renewal, and we have only sanctioned for 50%. And 50% only we have to 60 kg, and extra 50 kg still rail will be there track, and we cannot directly connect it. If that is the case, we have to separate, isolate it. So this will be 60 kg LWR and 50 kg LWR. In between you can go for combination SCG. Okay, but in one LWR we should not have two different rail section. Okay, for all you have to isolate, and we have to put a combination SCG in between 60 kg and 50 kg. Okay, LWR, CWR. And okay, in this case, suppose when we are not having this combination SCJ, and in another way we can do it. That means so 60 kg diagonal, 60 kg SCJ we can put, and subsequently we can connect this one, 50 kg track with the SCJ 60 kg, providing some combination fish plates. Minimum of putting, we call 3 rail panel in between that. So 60 kg is there, 60 kg SCJ we can put, and this side 50 kg LWR will be there. We can put 3 rail panel. Okay, we can put combination 60 kg and this one combination SCJ. Fish bed we can provide. Anyway, this is a way we can go for with different rail section when we have one stretch. And another thing, now whenever we go for TR or CDR, when new rails we are unloading and doing it, as far as possible, we should be free from the fish holes. We have to reduce the number of fish holes, because it is always prone for the fracture. We try to avoid fish holes, and we should put 1 meter long normally we are having, but it's slotted holes, and minimum holes we have to provide. Not okay. And so this case. And another thing I want to say here, earlier, in the first video I have been telling about the evolution of welded panel, and we used to get rails and all 11 meter, 12 meter, and subsequently we have 13 meter rail, and we're converting 3 rail into one panel, that's SWP, and subsequently we're solder welding it. But nowadays, nowadays we are getting a rails, 13 meter rail, and we are getting a 26 meter rail standard length we are getting, and also we are receiving 10 rail panel, that means 10 into 13, 130 meter rail panel, and 20 rail panel, that is 20 into 13 meter, that is 260 meter rail panel. So these are the different length, standard length we are able to get the rails, and for whenever we plan for a new line and gauge conversion, doubling and STR or CTR and all, as far as possible we are trying to get this 10 rail panel, 20 rail panel like that. Okay. But now this transport facility has been now slightly advanced, so we are able to carry a very longer panel because we are specially designed wagons we have through rails we are transporting, and okay, and also unloading also not like those unloading, normally 13 meter line we are side unloading will do, but in the case of a long panel we are having the end unloading, and for that we have special end unloading wagon we are attaching with it, we used to unload. Okay. That in all maximum PWA, permittive inspectors, and JEs and SOCs PV may be knowing about that. Okay. After unloading it, as far as possible, we should not have the minimum number of holes you must have when we are doing it. Okay. Using 1 meter long fish plate with the clamps as far as possible. Okay. This is something about it. And if at all we have there is no unavoidable, when you have the bolt holes, when it shall be chamfered, chamfering of fish holes also may be knowing. That is why chamfering means what normally fish holes, this will be sharp edge will be there, that we are blunting using the chamfering process, so that the stress concentration will be minimized. It's okay. If it is a sharp point edge, it results for the fracture. When it is blunting, so that corner is chamfered, when the expansion contraction is there will be or impact is there, the bolt hole, distribution load will be uniform, so you can avoid stress concentration in the corners of the hole, so that you can avoid the fish hole failures. That's why necessarily everywhere whenever we do this one chamfering and all, fish holes, and we have to do chamfering. This is something about it. And coming to the track structure, and see, this is a profile of LWR track. See here, this is the formation. This is the formation. This formation should be stable and having as per the standard profile. There should not be any cess erosion. If at all, if we have cess erosion, it should be made good before laying it always. Another thing, coming to the ballast. So ballast, this is a profile now we are supposed to follow. See here, this is our LWR track they are given 250 mm cushion. This is A is a cushion, 250 mm, 300 mm, 350 mm. So 250 mm minimum cushion they are given. Normally yard and all now 250. Of course, the minimum cushion, clean cushion you must ensure 150 mm. But 300 mm existing track normally is there. We are having the LWR, and 300 mm okay we can have. But whenever we go for the new track and new laying and this thing and all, and we must ensure 350 mm. Okay, 350 mm it is mandatory for the new track and all. And existing we can manage with 300 mm, and yard of course this one. Okay. However, for clean ballast of 150 mm must be there for proper packing. Okay. And coming to this shoulder ballast 350 mm. This is shoulder ballast. 350 mm we must have the shoulder ballast. And already we have discussed, in case of curvature, we must have 500 mm. That means extra 150 mm we are providing it, because shoulder ballast is very important, because the curvature, curving force and this one, and lateral support at the outer side of the curve, we must ensure properly the lateral distance. That is why we are increasing the shoulder width from 350 to 500. 150 mm extra ballasting we are giving it. Okay. But of course, in some cases already discussed, even then further hand arm we are adding it. Okay, in this case, some sharp curvature we are going, and also in the reverse curve portion and 100 mm, extra we are providing. That we should take care. And this is about the ballast, and 100 mm heaping up must be there. Okay. When earlier, no, before on normal track and all, no heaping up, but of course everywhere nowadays LWR only we have. But here, this is 100 mm heaping up. 100 mm heaping up ballast must be ensured. Okay, this is only don't slope. This is something about this ballast profile. And this is your ballast, crib ballast. This is crib ballast. Between the sleeper is called crib ballast. And shoulder ballast means what? This is both ends. Okay, this is shoulder ballast. Okay, the edge of the ballast, whatever given. This is even both crib ballast and shoulder ballast responsible for offering resistance. You see, but however, primarily the shoulder ballast is very responsible for the lateral resistance, and crib ballast response for the longitudinal resistance. Okay. So, in case of absence of shoulder ballast, there is chance for the buckling, because you just only holding the track frame intact to not to have any misalignment or buckling and all. So it should be, in this case, the shoulder ballast is very important. There should not be any deficiency in the shoulder, and we should suppose follow the profile as per the standard profile given. Okay. And in case of crib ballast, this longitudinal resistance, because for example, in case of any absence, this deficient the crib ballast, in case of any rail fracture, since of lateral resistance, longitudinal resistance, will be less, and ultimately more expansion, contraction, more gap will be there at the fracture point. At the same time, breath length also, when there is no proper crib ballast, that length of breathing will be more. Ultimately, the more gap will be at the SCGs. So this is why this is a crib ballast and shoulder ballast. Okay, the functioning. Our both crib ballast respond for the both resistance. Okay, but primarily I am telling this one. And this is about it. And of course, sleepers nowadays we are going with the standard, PSC sleepers. We are going standard sleeper. And of late we are having welded base sleepers. Having welded base to offer more resistance. Okay, and also rail and sleeper we are providing rail and all this one elastic fastening with the proper reparable liner. So these are all the track structure we are supposed to ensure. Our rail is concerned, minimum 50 kg rail we are supposed to use it. Okay, this is something about the track structure. And another thing, off late, this LWR on the ballastless track. We have some places we have introduced some ballastless track also. In this case, as per the latest corrections, they have given some stipulations. We are supposed to know this one. Okay. In this case, fastenings to satisfy test plan criteria for longitudinal resistance 15 kN per meter per rail. What is ballastless track? See, normal track, we have a standard, ball formation, ballast, steeper, and rail, and with elastic fastening, fixing and all will be there. But here it is no ballast. Completely it is the foam bed. That's specially designed sleeper will be there, and connected and the rails are connected with the sleepers, and there is no ballast at all. But anyway, here due to the absence of ballast, but the sleeper has to offer some resistance. Okay, so that is why in such a way designed for offering the longitudinal resistance of 15 kN per rail. Okay, this we are supposed to ensure. And minimum rail section above 60 kg, and permitted here sharp curve is 350 meter only, and steepest gradient is 1 in 80. Okay, 1 in 80. This we must. And ballast retaining wall, what you do 100 meter in ballasted. What do you call this one? See here, this is already this you have seen. And ballast retaining wall here, because this is a ballasted track, this is ballastless track. Definitely, suddenly we are coming from ballastless to ballasted to ballastless. So definitely this portion will be disturbed. Okay, some ballast deficiency, because of sudden change, we must ensure the proper ballasting here. Okay, so that is, we must provide a 100 meter from the junction of the ballasted track and the ballastless track. 100 meter we have to provide a retaining wall. SCG to be located at a BT ballasted track 30 meter from the junction of the junction of the ballast track and BT. This is the junction of the ballast track and ballast. Here SEJ we must have only in the ballast track, where we have the ballast. No, that track only you must have the SEJ. That should be 30 meter away from the junction. You must have the SEJ. And SEJ movement is less. That of course we have SEJ movement is less in the ballast track side as compared to the BT. Here, because we are designing for 50 km per meter, right? Because normally in our case 12,000 12 km will be. That is why the movement will be less in this ballast track compared to the ballast track. Okay. Okay, these are the instructions available. Just we can note down all the points. It will be helpful for answering your multiple choice questions and all. That is why I am just highlighting it. And anyway, we are going to see in the quiz also. Just included in the application. Okay, you can this one. And the creep to be checked for 500 meter from BLT and at an interval of 100 meter. Okay, this ballast track, we have to check the creep. Okay, up to half a kilometer, 500 meter. Okay, every 100 meter, we have to erect reference pillars and we have to check periodically and see that any creep and all. We have to check up. If there is with reference pillar, the movement of movement is more than 10 mm, then we have to plan for desourcing for 1000 meter. Okay, this is something about a ballasted track, ballastless track. This one, and recently this correction slip has been given and it has been added in Internal Promotive Manual. Okay. And wherever wherever LWR CWR is followed by fish plate track. Suppose we have LWR CWRs, okay, then some portion we have sharper curvature is there, or otherwise we are approach of this one, some station something, and we must have necessarily fish plate track SWR. In this case, this should be isolated. This same structure we must have whatever LWR CWR is having. That should be continuing for at least 3 rail lengths. Okay, beyond the SEJ. So SEJ is there, and beyond that same track structure you must continue for 3 rail lengths. Then your SWP and fish plate track, whatever you have, you should be ensured. At any cost, the LWR, level crossing should not fall in the breathing length. As I already told you, breathing length is meant for breathing. We should not have any level crossing in the breathing length, because once the level crossing, it is a fixed, fixed structure, and that will not permit any breathing expansion, and ultimately the force will be locked up at the approach and results to any kind of failure or buckling or fracture. That is why we are supposed to ensure this one. At level crossing, we should not fall in the breathing length. Such a way you have to design your LWR when you are laying it. Okay, so doubly providing the SCG, the locations. This is something about it. And points and crossing, of course, see, normally points and crossing will be in the station only. Approach of the station will come across. See, normally we are terminating the LWR and the approach of the this one points and crossing. Duly giving the isolation. Okay, this should be followed. This already provided well anchored, and with the elastic fastening and all. Okay, that should be there. Okay, this is one. This should be like that. Suppose we have the LWR here, this is the points and crossing. What will happen? See, this isolation should be 39 meter in between. Okay, 3 rail length. Normally, you must ensure this. We are terminating our LWR here. These are points and crossing in between the same track. We must have 13 meter isolation must be there. Okay, same structure of the LWR must follow here. Okay, like that. Suppose you want to continue isolating the points and crossing, we can continue your this thing. Okay, this is something about it. Okay, suppose you want to carry through LWR. Okay, because why you are not taking through our LWR on the points and crossing? Because of the discontinuity. Because of the normally LWR in LWR means there should not be any discontinuity. It should be continuous. Continuity we must ensure every point. Because fish plated joints, it will allow expansion control, and full of force will be there. The fish plate bolt will not be able to take that much force. It will fracture. That is why we should not have any this one discontinuity in the LWR. But in the case of points and crossing, we have discontinuity where it is there. Discontinuity, the switch portion we have the discontinuity. I mean the heel of crossing, suppose this is one rail through a length, okay, no problem. This completely we are welding it, continuity. But here this says, see, here it is a switch rail, it is a, this is your switch portion, this is your stock rail, this is your tongue rail. This continuity is not there. Here there is the discontinuity. At the same time, crossing also will have the discontinuity, okay, will be there because of CMS crossing we have, and we cannot, we are not welding it. Normally we are providing only frozen joint here, okay, like that. But if you want to carry the LWR, and there are some instructions that is given in the CT48 report, following that you can carry through. But in this case, what they say, would strengthen the points on crossing. Particularly as I told you, this is the discontinuity portion. The discontinuity, here discontinuity, here we are providing a stress frame like one anti-grip device. We are providing it so that it will ensure the not permit any longitudinal movement. It will as if it is a one rail piece, okay, one rail. So that will they are providing, and also instead of normal CMS crossing, we are going weldable crossing. So once weldable crossing we are providing, we will be able to weld the joints. Here nowadays we are providing only frozen joint, gapless joint we are providing, ensuring CMS crossing. But when you are using weldable crossing, we are able to connect this one and avoid the discontinuity. So here once we made a discontinuity, okay, we can take the LWR and following other instructions. Lot of instructions they given, not only this one, and we have to strengthen the points using special fastenings, fittings and all, okay, everything. So that report CT48 contains the this one complete details, instructions what we are supposed to do in the points and crossing when you want to take through LWR over the points and crossing. Once we take through the LWR through the points and crossing, okay, continuously, even through stations, that's called CWR. But terminating up to this one is called LWR. When you are even continuing through our points and crossing and station, that is defined as a CWR. Okay, this is something about it. Another this thing, in a yard, station yard and all, normally, so we'll have the insulation joints, not only in the station and also in the automatic territory and all, we have, everywhere, insulation joint for the signaling purpose, okay. So as I told you, the LWR should not have the discontinuity. Once discontinuity is there, it will not function as a LWR. But anyway, here we have to provide a insulation portion and insulation pad, and we are now there is a discontinuity. However, we are providing insulation, but rail is cut, and we are providing insulation and joining like that. But see, however, though we are providing this one, and this joint should act as one piece, okay, like a monolithic. That is why we are going for the wherever we go for insulated joints, we are providing for G3L type insulation joint, insulated, okay. It's got a glued joint, okay, glued joint. Here it is specially designed. It will not allow any movement, okay. The joint should not permit any longitudinal movement, okay. It is firmly fitted so that it will act as a one rail piece and a monolithic piece, okay. So such a way it has been designed and manufactured. We are providing 6 mm. This is the insulation pad. It will not allow the current from this end to that end. That's why we are putting insulation. And here also 1 meter long plates normally it is there. It is all manufactured in the workshops. Okay, here we are providing insulation, channel and glass cloth carrier and applying glues, okay, and fitted. But whatever bolts we are providing, it is high tensile bolt, not like ordinary. Since we are providing an LWR subjected to lot of forces, tensile force, heavy tensile force, it has to take that much tensile force. That is why we are putting high tensile bolt. We are providing it, and also the holes also such a way designed not to permit any movement. Because in ordinary fish plate, there is a play in between between the bolts and bolt hole and the fish plate. All will be different diameters. Bolt hole diameter is different from fish plate diameter and the fish hole diameter, the rail fish hole diameter. Since we are having different diameters, it will allow some movement. There will be play and it will permit some movement. So because we are designing for permitting expansion contraction. But here it is not so. exactly we are the holes of this one rails and fish plates and bolt and all same diameter, so we do not allow any play. At the same time some allowance is given for providing ferrules and all, okay, insulation ferrules, so that it will not allow any longitudinal play, longitudinal movement, such a design. And also it takes care of the complete tensile forces, such a way it is designed providing HTLS bolts and completely glued to act as a monolithic piece. Okay, this is the type of joint we are supposed to use in a LWR wherever we want to have the insulated joints. It's called glued joints, G3L type. Okay, this is also you should note down for the examination point of view, and others PV engineer may be knowing, and others they should know about it. Okay. And coming to the location of SCJ, already we have discussed, we must properly taking into all obligated point suitably to locate the SCJ. And also the regarding SCJs, switch expansion joints, where it is supposed to be located, and normally we should not, this SCJ should not fall in the transition portion, and SCJ should not fall in the curvature sharper than certain degree they are given. Okay. See the conventional SCJ, this is 4 series, 4160 and 4165. Okay, 50 gauge, 60 gauge, like that. With the straight tongue rail, stock shall not be located on the curve sharper than 0.5 degree. Only we can provide the SCJ of this type not sharper than 0.5 degree. Okay, the curvature only we have to provide, and also it should not be fall in the transition portion. Okay, why transition portion? See, transition portion we are providing supervision. The base rail is inner rail, that is horizontal, and the outer rail will be we are providing supervision easing out, so that it will be like a ramp increase, so that there is a chance for since the plane is different, chance for lifting tongue rail. That will affect sometime it may traffic, moving wheels may affect the tongue rail and hit and get damaged. So that is why normally we don't permit the locating our SCJ in the transition portion, and if you can permit in the curve portion, circular portion, so that even though there is supervision, it will be uniform. Okay, only level difference, but uniform level will be there. But in the first case 4160, conventional SCJ we are supposed to permit only in the curvature not sharper than 0.5 degree. And also now recently we have the special SCJs, we have been now improved SCJ. Okay, we have 6 series, 6902, 6914 and 6922 and 693. It's two types actually. This is 50 gauge, this is 50 gauge. Two types of SCJs, improved SCJs we got. That SCJ we can permit up to curvature of up to 2 degree can provide. Okay, even beyond that also now recently it has been designed 4 degree curve for 4 degree up to 4 degree improved SCJ. That is drawing number 8926. Here 8 series is only 4 degree, 6 degree only 2 degree, and 4 series is only 0.5 degree. Okay, these are all the different SCJs we can use, but there is a limitation we are using in the curvature according to the shortness. Okay, this is the last one, 4 degree improved SCJ, 60 initial gap 65 mm. The earlier case and all 40 mm initial gap we are providing, but here it is 65 mm maximum gap. Drawing number this one 60 mm maximum gap, this one. These are all 80 mm maximum gap, and initial gap 40 mm. This for 50 kg only with the approval of CTE we can use. Okay, this is something about a different SCJs what we have. Okay, we will see again SCJ shall not be located in the transition as already discussed. Okay, this is different type of SCJ. This is a conventional SCJ you are learned all. This is only stock rail, this is tongue rail. Okay, this is only the one gap will be there. Normally this is a special SCJ sleepers we are having. We are providing some angle also to avoid any outgoing sleepers going out of square and maintaining the sleeper spacing and all. Okay, this is this thing. and we have the reference pillar. It is not, reference line will be there, and this thing and all regarding in measurement all I will discuss in the next videos about doing the discussing about a desourcing operation. Okay, this is one type. This is 4160 and 4165 50 kg 60 kg. This is a conventional type. Okay, this is a tongue rail, stock rail. This is having the permit in the expansion contraction. Okay, this is actually earlier and all initial cap 60 mm, maximum design for 120 mm, this type of DCJ. Nowadays and all we are providing only 40 mm initial cap and design is 80 mm this cap. Okay, this is a conventional SCJ. Approval for laying. See, coming to the approval for laying LWR CWR. See, whenever we want to plan LWR CWR from X to Y, proposal we have to initiate and it should be submitted to CTE for approval. Approval of CTE, then we can go for this one. And detailed plan, we have to submit and showing all details of this one. In between A, X and Y, what are all the structures such as we have profile and signal positions, curvature, gradient, everything we must. And it should be plan should be prepared in 1:5,000 in the horizontal plane scale. So we must prepare and submit to the CTE for approval. On approval of this thing, you have to go for this one. Existing this thing, of course, okay, but new line, new LWR or CWR we want to propose, and you have to go for the approval, and after getting the approval from CTE, you have to plan. And coming to any deviation from the provisions of LWR manual, approval of PC is required. This they also must have. This again. This is actually the proposed what we are sending. It is available in the Indian Rail Permit Manual. These all details we must give like profile and gradient and whatever your station over this one gradients, everything showing bridges, all these things, track switches, station, everything, and height of the canteen area. This thing, all these things you have to ballast cushion how much. And what is the existing track, tracks, rail sleeper fastenings, and position of the signal and insulated joints wherever we have, and where you are going to plan ACGs and all, okay, and proposed ballast cushion, any rehabilitation work in progress or it is to be undertaken. So any weak formation is there, okay, and proposed all these things we have to put in the plan and preparing 1:5,000 horizontal scale. We have to submit to the CTE for approval. Okay, this one, we are newly converting SWR into LWR. This thing we have to follow it. Okay, and laying of LWR CWR. See, already whenever you want to do lay our LWR CWR, converting the existing SWP into LWR, first we have to do complete survey of the section proposed for laying LWR CWR. Okay, completely we have to do collecting all details what is required for sending our proposal, and all the deficiencies shall be made good before laying LWR. So whatever deficiencies already rehabilitation work, anything we have to complete it, and any realignment occur we have to plan and that should be completed. Any assess making of work, okay, all any rail renewal, all these things, any deficiency whatever we have, and through fitting renewal, whatever we want to do, so fitting should be intact. So all these things we have to before converting LWR, we have to complete and make good, okay, and for laying LWR. And for laying LWR, you have to keep all the materials and equipment, whatever welding equipments, welding material, all these things, and other all materials required for renewals and all. You have to keep it ready for carrying out this one, LWR. Then laying, suppose A to B, we want to lay LWR. Normally, we must have any 3 rail panel or 10 rail panel, 20 rail panel. Suppose 3 rail panel already we have, normally we should not convert directly from free rail track. Normally, free rail track normally we don't have. If it is there, we have to convert to 3 rail panel and then LWR, like that. Suppose already we have the SWP 3 rail panel and we can go for this one. And suppose we are doing CTR, TRR and all, unloading our 10 rail panel, 20 rail panel, first we will complete this one, and finally we have to build all the rest of the fish bedded joints, like that we have to do it. Suppose we have the station, the stretch in between A and B, we want to convert into LWR after this one. This is our this one after doing our TRR or CTR or laying a new track First, we are providing with the fish plates. Normally 1 meter long fish plates, we must have this, when you are reducing the number of fish holes, okay, using clamps and all. Okay, first we have to do it. And subsequently, this is a stretch we want to have. First we have to locate the SCJ point, and we have to insert the SCJ along with the 4 meter cut rail. We have to do it. Okay. Then what to do? Then after that, this in between we can weld all the joints. In between we have to weld all the joints. And after that, we have to do the de-stressing. Okay, the de-stressing of rail should be done. So normally de-stressing maximum 1 kilometer. Normally it is advisable to cover. Then only it will be the proper stress. Releasing of forces will take place. Maximum 1 meter, 1 kilometer length. So after doing the de-stressing, what will happen? There will be change in length here. The gap will be more or less because of locked up stress is tensile force. Normally it will contract. The compressive force, it will expand. No, there will be a difference in length. And also we have to adjust the SCJ now. We have to adjust the SCJ here, the gap. We have to keep the SCJ in mean position with reference to and reference pillar to be erected and marked. Okay, SCJ after, because correct initial gap is because when we are doing de-stressing, it is a TD temperature. We are doing the de-stressing, and the gap should be at TD initial gap of 40 mm. We are setting it, and after that what we are doing, we have to measure the resultant gap and put the rail and okay, this duly giving the allowance for welding under 20 mm giving allowance, we have to put the rail, and finally we have to weld all the joints here. Okay, that's all the joints. Something about, suppose if it is 1 kilometer means 2 SCJ will be there, because okay, if suppose it is a 5 kilometer, what will happen? So this is SCJ location, but only 1 kilometer we have to go. Okay, after that we have to do de-stressing. This side we have to adjust the SCJ, and this side we'll have some closure and all gap will be there after de-stressing, and subsequent portion you have to take up this 1 kilometer and again do the de-stressing here, and this side okay, keeping a correct gap, and we are welding it, and we have to localize, equalize the force by doing the local de-stressing. Like that continuously the process should take place. De-stressing this portion 1 kilometer, de-stressing this portion 1 kilometer, like that we have to go till the other end. Okay, finally when going this here, here we have to remove this one, and we have to adjust the SCJ doing the de-stressing, and we have to fill up the gap and weld it. Okay, this is the procedure for laying a WR, CWR. Just I am telling you, almost permitted engineers who are on the field may be knowing about this one, and this is the idea I am given for others who are not knowing this one. Okay, so this is about the laying of LWR, and okay, I think this will be useful for you. I hope that I explained to your requirement, to your satisfaction. Thanks a lot, and with that we will conclude this laying of LWR, this portion, and next slide. Okay, next video I will discuss something about the maintenance operation and de-stressing operation. Okay, thanks a lot. Thank you.